Alison received her PhD in chemistry from the University of Melbourne in 2002. After working as a postdoctoral fellow at Brookhaven National Lab with Dr. John Miller in the areas of electron transfer and radiation chemistry, she returned to the University of Melbourne, where she worked with Professor Paul Mulvaney in the area of nanoscience. In 2010, Alison moved to Monash and was awarded an ARC Future Fellowship in 2011. Her research focuses on the energy transport and optical properties of well-defined assemblies of nanoparticles, including metal nanocrystals and semiconductor nanocrystals, as well as charge and energy transfer within nanoparticle organic systems. Today she's going to speak on the many colours of gold.
So the theme continues. Michael was talking about graphene, which is very small in one dimension, and I'm going to extend that to talking about systems that are very small in all dimensions. Not quite as small as atomically thin, though. So I've titled this The Many Colours of Gold, and unfortunately I didn't have many gold bullion bars lying around at home, so I've taken this photo from Wikipedia. In fact, I don't even have one. But what you can see is a metal. It's gold. There's a metallic luster because of the absorption, and what you're effectively seeing is the reflection of the electrons, and we're all fairly well aware of the colour of gold. I've also got some other white gold on that looks white, but that's not the effect I'm going to be talking about today. So, the many colours of gold. I'm a chemist, so we think in terms of atoms, and so I have here a picture with some atoms, or circles. They can be any atoms you like, carbon or gold. And you can see I'm only starting with 9, very, very few atoms, but we're going to build them up. And so we can take those atoms and we can turn them into molecules. Here are some very small graphene sheets known as naphthalene. We can have other structures. We can have some semiconducting ion pairs there. But what we observe in the bulk are these sorts of things. So we observe gold as these bars. It's reflective. If we build up our organic molecules into a lattice and then crystallise them, we see crystals. But there's a very interesting property, and it occurs before we get to this bulk, and as we start to build a number of different molecular units or atoms together. And so if we were to stop our growth of our gold, for example, if these were gold atoms, and have somewhere between hundreds and thousands of atoms, we see some very, very different properties. And the same thing, if we take some very small particles of some semiconductors, cadmium selenide, zinc oxide, even silicon, and we stop there and we have some very, very tiny particles of our bulk, it doesn't look like bulk anymore. And so, in fact, if we build up our gold slowly, and I'm a chemist, so we build it up, but you can also break it down from the bulk gold if you wanted to, and you can make red gold. So this is a solution of gold, very, very small particles, and these ones are about 17 nanometers in diameter. They're spheres, and you can see that they're a ruby red colour. They're transparent. You can see through that solution. It looks like red glass. In fact, the red glass in stained glass windows of old was often from gold impurities. It's added as a dopant when that glass is made, and that's what gives the colour. Now, if we go back to the idea that we're building up our gold, we start from a single atom and we build it up into something that's a molecule, or it might be a complex if we're talking about a metal. And we have those discrete energy levels for our molecule or our complex. We add some more gold atoms, or we could add silver if we're making silver, it doesn't really matter. And we get a cluster. The interesting thing is in between this transition from the cluster to the nanoparticle up to the bulk gold, you get gradual changes in properties. And colour is one of those things that does change. At the very small sizes, you see quantization of some of those properties. And you might have heard of quantum dots. That's where that term comes from, quantization of some of the properties of that material. And the things that can change are the colour. Catalysis. Gold, if you make gold particles small enough, it actually acts as a catalyst. You need it very small, but it does catalyse things. Now we know gold coins, they don't react. They certainly aren't catalysts, but if you make gold small enough, it does become a catalyst. The surface area is highly important. You've got a very large proportion of the atoms at the surface of those molecules or nanoclusters, and that's very important. As you go to these very tiny sizes, the hardness of the materials change, the electrical properties, the conductivity changes, and we've heard some nice examples of some of that. Tensile strength can also change. And so in this regime where we transition from the molecular stage into the nano stage and through into the bulk, there are some very interesting changes that occur. Here are some more gold, and it's not quite as clear as I might like here. These are gold nanoparticles, and we'll get to the nano shortly. And all that is changing here, it's all gold, every single one of these solutions, but we're growing the gold atoms into little tiny nanorods. And here's an example image that was taken with an electron microscope to show. You can see this scale bar is 50 nanometers. They're about 50 nanometers long and about 15 or so wide. And the colour change that occurs, this solution is purple, this is blue, this is red, and this is a brown colour. I've been talking about gold because we like to think of gold as well. Gold, it's precious. Silver does the same sort of thing, as do many other metals, copper, palladium, aluminium. Here are some silver nanorods, and you can see again, as you change the length of that nanorod, you change the colour. So let's get to the nano that I was mentioning, because this is effectively the area of nanoscience. We know meters, we know millimeters, no problems. Here's our ruler with some millimeters on it. Now, if I were to say micrometers, you'd be reasonably familiar with that. That's the size of a blood cell or a virus particle. They're of the order of 1 micrometer, a tenth of a millimeter. Oh, sorry, a thousandth of a millimeter. A nanometer is 1,000 times smaller than a micrometer. 1 by 10 to the minus 9, sorry, it's slipped down there. And here are some images of, these ones here are actually gold nanoparticles that have been synthesized. You can see they're crystalline, and they form various shapes, and you can change the shape depending on how you choose to synthesize them. These are actually very large for nanoparticles, and the scale bar here is 500 nanometers. These large triangular prisms are about 300 nanometers, so 300 by 10 to the minus 9 meters in side length. To put this in perspective, this is an image of a human hair. It's been zoomed in on, of course. So you take your hair, take a section of it, take a picture of it. It's about 80,000 nanometers wide. So 1,000 nanometers would be this tiny spot on it. So we're talking about very, very tiny, tiny particles. So what's a colour actually from? And there are actually 2 regimes. If you get the gold clusters small enough, as I say, you get into areas where you have quantized states. And then if you move up from there and get them slightly bigger, then in that stage you see colour changes, but they're due to a different phenomenon. From about 10 nanometers upwards, the colour is due to the localized surface plasmon resonance. So here is our gold. As we can see, I've made it gold, nanoparticle. And as it's a metal, we have free electrons associated with those nuclei. And I've overlaid my free electrons in a cloud of red. They interact with the light, the electric field of light. And as the electric field of light impinges on this metal particle, the electrons react. And they react in phase with the oscillation of the electric field, or the wavelength of that light. And so, if you can see the red cloud goes up and down, that oscillation across that particle is known as the localized surface plasmon resonance. Let's break it down a little bit. Here's another one. At one extreme, we have the electron cloud displaced as far down as it can physically get because it's confined by the material. It can't move any further. And that gives us a slightly negative charge on one side of the particle and a slightly positive side on the other. So it's a dipole. The positive charge acts as a restoring force for those electrons, so they oscillate back across. And you get the opposite situation. So you effectively have an oscillating dipole that is forming. And that occurs at a given frequency of light. The light that you see is light of the wavelength that doesn't get through the sample, so the light that's absorbed. What's left is what you see. That's what gives the colour. So if you make them a different shape, and here I've got something approximating a gold rod, then you have two different axes of electron oscillation, and therefore two different frequencies at which these particles absorb light. Because of those two different frequencies, you get different colours. And so you see physically in the solution those different colours of light. Now, I've got an image here, and these are glass slides. They've got some conductive stuff on them, so we can look at them in an electron microscope. But on the top of these slides are single gold nanoparticles. You can see you've got no hope of seeing them with the naked eye, absolutely none. They just look like glass. The black dots, not gold nanoparticles, texture, so we can tell them apart. So if you take these slides that look like this, and you put them under a microscope, what you see is scattering of light of different colours from points on that surface. And that's what we're seeing here. This is an image, it's called a dark field microscope image. The black is where there's nothing. The little dots are where there are metal nanoparticles, and these are gold. This particular one has some gold spheres, they're the green ones, and some gold rods, and they're the red dots. And so we can actually see, using optical means, the colour of single nanoparticles. And we can then take the light from each of these single ones and get the spectrum of it and see the surface plasmon resonance. I'm just going to end with these two images. And this is a high resolution transmission electron microscope image taken at the Monash Centre for Electron Microscopy. And you can see in here, what you're seeing is each dot is an atomic column for these gold nanoparticles. The scale bar here, this is 1 nanometer. And so you can see we're looking at these are the atoms that make up those gold particles. Even the nanoparticles that I'm talking about, they've got a lot of atoms in them still. The others, they're the ones that show the quantization and the effects are due to different things. So I'll leave it there. Thank you very much.